Hi, and welcome back to this introduction to dApp development. In the previous episode, we looked at what an indexer is, and we used some data from a public indexer to display blockchain data about the user in our dApp. In this episode, we're going to discuss smart contracts. We're going to look at some examples of smart contracts, and then we're also going to deploy some to Ghostnet. So, to break it down a little bit, in this episode, we're going to learn what are smart contracts. We're going to look at a simple example of a smart contract, a hello world, so to speak. And then we're going to deploy that to Ghostnet using Octez. We did briefly discuss Octez in episode 2, but Octez is essentially a client that allows us to talk to a Tezos node. And then we're going to look at something called the FA2 standard. And we'll briefly discuss the concept of NFTs. And then we're going to look at a simple and full example of an FA2 contract. And then we'll have a couple of brief slides at the end talking about gas fees and security considerations for smart contracts. Okay, so here we are again, our old friend, the architectural diagram. And this is where we're focused today, episode 6, smart contracts. So if you can remember, the smart contracts are represented by these little icons here and here and here. And smart contracts are programs that run on the blockchain. They're programs that run on the blockchain. I'm repeating that because it's easy to get maybe a bit overwhelmed by some of the terminology that's thrown around in Web3. But smart contracts are simply just programs that run on the blockchain. And we'll see how simple some of those programs can be in a couple of slides. So as I said, smart contracts are just programs that run on chain. Smart contracts, in a more technical sense, are actually a type of account. So we looked at Tezos accounts earlier, and there are different types of Tezos accounts. And a smart contract is a type of Tezos account, and they have a balance and can send and receive Tez like a normal account, but they also have code associated with them. So that when I said originally that smart contracts are programs that run on chain, smart contracts really are accounts that have a program associated with them that runs on chain. But it's not any more complicated than that. So looking back at the program part of the smart contract, smart contracts have entry points and they have storage. So what is an entry point? If we think about a smart contract program in a similar way to a Java class or a C# class or a class in any other object-oriented language, an entry point is a little bit like a public static function. Or in fact, it's a lot like a public static function. So it's a function that can be called by some kind of external program. In the context of smart contracts, the thing that will invoke an entry point is a Tezos account. And some entry points will update the smart contract's internal state. Apologies for the missing apostrophe in smart contracts there. I've only just noticed it. But some entry points will update their internal state. And that internal state is called storage. And you can think of it, again, with a Java class or a C# class, just a bit like private variables. There are different programming languages that can be used to write smart contracts on Tezos, including SmartPy, Ligo, or even Michelson, which is the kind of low-level language that SmartPy and Ligo will compile down to. So on that note, let's have a look at writing our first smart contract. So we're going to use SmartPy. SmartPy is based on Python. It certainly has some differences from Python, but it's heavily based on Python. And in fact, for the basic smart contracts that we're going to write, it will look very, very similar to Python. So I'm not going to lead you through the entirety of writing smart contracts because that's not really what this course is about, and it certainly deserves a course in its own right, and there are many courses out there that cover this kind of thing. So we're just going to do a little bit of a whistle-stop tour of what smart contracts are. So if I'm skimming over some of the concepts, that's kind of on purpose. Hopefully this will give you a good overview, but if you really want to understand more about how to write your own smart contracts, certainly look for other courses. But there are many dApps out there that use smart contracts that have been written by someone else. And so you just need to deploy your own version of that and then build your dApp around that ready-made smart contract. Here's the SmartPy documentation, and it explains how to install SmartPy and how to run SmartPy to compile a smart contract that's been written in SmartPy. So smartpy.io/manual/introduction/installation is where you would find this information, but I've already set up SmartPy. So let's jump over to the basic smart contract that we're going to walk through here. So here it is. There isn't that much to it. In fact, the core logic of the smart contract is just these few lines here. Everything above it is boilerplate, and everything below it is unit tests or tests. So actually, the logic is very, very simple. So let's see what our smart contract is doing. So firstly, the smart contract is just this class here. So when I've been using an analogy of a class earlier, part of the reason is because it explains it well, and part of the reason is because in many programming languages that write smart contracts, they are literally defined as a class. So we're calling our class simple greeter, which is just the name for our smart contract. It's an informal name. And then we have our constructor, where we are setting our storage. So our storage here is everything that is within self.data. So the storage for this smart contract, it's just going to be a single field called greeting, and the value that it's going to be set is a parameter from the constructor called greeting. And this concept within the world of smart contracts is that you can initialize the storage when you create the contract with a certain value. So when we create our smart contract, when we actually deploy it onto Ghostnet or mainnet, we will provide it with an initial value for that for the storage, and that is what is represented by this parameter here. Okay, so in terms of the core logic inside this class, we've had a look at the constructor, and we're now going to have a look at these two things here, number 1 and number 2. The first thing you might notice is they've got this decorator here. And all that this decorator is saying is it's telling SmartPy that this is an entry point. So this is a function that should be exposed publicly so that we can call this entry point from our dApps. So as opposed to any other function that we might define, which we would want to be private and we wouldn't want to necessarily be callable from a dApp. So, so this is an entry point, and the entry point is called replace, and it takes some parameters, and all this entry point is doing is it is replacing whatever was in the state before with whatever is passed in from the parameters, specifically whatever is passed in from the text part of the parameters. And then our second entry point is doing something similar. It's called append, and instead of replacing our storage, you can see that it is appending to our storage, and it's that simple. So at the bottom here, we have some tests. And these tests set up a testing scenario. This line is boilerplate. This line is simulating creating a smart contract, or to use a technical term, originating a smart contract with an initial storage value of hello. So that's what this is. This next line is more boilerplate, just setting up the testing framework. And then the first thing that we do is we verify that the storage has a value of hello, which it should do at this stage because that is the storage value that we originated the smart contract with here. And then we run the replace entry point with text value of hi. And then we run the append entry point with text value of space, comma, there. And then we verify that now the storage has been updated to read hi there. Pretty simple, and hopefully that explains some of the basic concepts of a smart contract. So what we're going to do now is we're going to compile this smart contract. And when compiling the smart contract, it will run these tests as well. So if there was any issues with that test, it wouldn't compile properly. So I can literally just run this command here, smartpy.test sc.py compiled. So that all that's saying is run smartpy on the file called sc.py and put the compiled code into this directory called compiled. Now it's compiled and we can have a look at what we have. Now, again, the details of this, I'm not going to go into in too much detail, but suffice to say is that these are the files that have been compiled by SmartPy. I'm going to do a small side note on the naming convention of these files. It's certainly something that you should read up about a little bit more. But step 1 and step 3 refer to the different compiled files as a result of when it compiled this verify scenario versus that verify scenario. So this is scenario 001 and this is scenario 003. But you'll have to read up about why it's called 01 and 03 separately. It's not something, if I'm 100% honest, that I have totally got my head around yet. So I don't think that I should be trying to explain it on this video. So now that we've compiled it, we can now deploy it to Ghostnet, or to use a technical term, originate it. So I'm going to cd into the compiled directory and into the simple greeter directory within there. And then I'm just going to zoom in a little bit just so you can see a bit better what I'm doing. I'm going to run an octez command. So let me just drag this up a bit so you can see more easily what I'm doing. So the command to deploy a contract is as follows. And you will have needed to have installed the octez client yourself. Again, this is something that there's plenty of documentation on how to do this. So now that, because I've got the octez client installed, I can run octez client. Then I'm going to specify which RPC node I want the octez client to speak to. And then I'm going to tell it that I want it to originate a contract. I'm going to give it a name that it doesn't particularly matter. It's just a name that is used by the octez client itself. So it just needs to be one that I haven't used before. So I'll call it simple contract 1. I don't need to transfer any Tez to this contract. So I'm just going to say transferring 0. And I'm going to originate this contract. The owner, or the administrator of this contract is going to be the address that the Tezos account that we've been using throughout this course. The alias that I've given to that account in Octez is Ghostnet account 3. So that's what this means. And then we need to specify the name of the file of the smart contract, which is running, and then it will be this, no, not this one, sorry, the one that ends contract.tz. So step 1 cont 0 contract.tz. And then I'm going to initialize it with some storage. So I'm just going to check that this storage.tz file, contains the initial storage that I want it to have, hello. Now we can change this. So let's have it as hello, Olly. So back down here, I'm going to say that I want to initialize it with the contents of this file, step 001 cont 0 storage.tz. Step 001 cont 0 storage.tz. Right, so if I run that, let me just check that I don't have any typos. I think I've got one typo here I'm missing. speech mark. Let's give that a go. Now, you'll see an error here, and the error is saying that I didn't specify a burn cap. I basically didn't specify how much Tez I'm willing to spend on originating this contract. The reason that I didn't put it in to start with is that I didn't know what the burn cap would be. So the only way to find out how much you need to spend is by actually running this command. So let's now run it again, but append it with this burn cap as suggested by Octez. And you can see it's doing its thing, deploying to Ghostnet, and there we go. If you look at this line here, this is the important line. It says new contract, and it has the address for the contract originated. So if I copy that contract address, and then I go back to my browser, and I go to tzkt, not the API documentation, but the ghostnet.tzkt.io, which is a place where I can look at details about any smart contracts or accounts that I might be interested in. If I go there and I search by the contract address that was just output from Octez, you'll see that my smart contract's here. So we can have a look at the code. And here we have the code. And here's the storage. Oh, it says hello and not hello Olly. I wonder why that is. That's why it is, because I didn't actually save the change there when I changed it from hello to hello Olly. You'll have to trust me that if I had saved this before we deployed, it would say hello Olly here and not hello. Anyway, and the entry points you can see here. So there is an entry point called append that takes a parameter string, and an entry point called replace that takes parameter string. If we go back to the operations tab, we can see that we have only had one operation so far, which is the origination operation or the deployment operation. But now users from their dApp could call these entry points. They could call append and replace, and we'd start seeing these operations stacking up here, and we would see the storage changing accordingly. But we will save that until a couple of episodes' time when we actually start integrating our dApp with an RPC node and start calling entry points. Okay, so now that we have an understanding of what a basic smart contract might look like and how to deploy it, we're going to talk about tokens, including NFTs, and the FA2 standard in Tezos. So in Web3, assets are represented as tokens. You might have heard of the term NFT, which stands for non-fungible token. The two basic types of tokens are non-fungible tokens and fungible tokens. The concept of fungibility is not a term or a concept that is specific to Web3 or blockchain. It's actually a financial term. I'm not going to go into the details of the difference between fungibility and non-fungibility, but suffice to say that cryptocurrency is an example of a fungible token, and a unique non-fungible tokens are unique. They're necessarily unique. That's what non-fungible means. Now, the FA2 standard in Tezos is one which defines the names and behaviors of certain entry points and storage for contracts that implement tokens. Now, what that really means is that FA2 is a standard that was written so that the entire Tezos ecosystem can talk about tokens in the same way. So the FA2 standard defines how smart contracts should be structured, so that the rest of the ecosystem can consistently write programs that will be able to interact with contracts that are representing tokens. So what that really means, as this fourth bullet point here says, is that for a contract to adhere to the FA2 standard, it needs to have certain entry points with certain names and certain parameters, and its storage needs to be structured in certain ways, such that any tokens that are created by that smart contract can interact with all the different dApps in the Tezos ecosystem. So within the FA2 standard, NFTs are represented just as IDs in the smart contract storage. They're IDs that are associated with the owner's address in the storage, along with some associated metadata. So without the metadata, the NFT doesn't mean anything. The metadata could include an image that this NFT represents, or some kind of other textual metadata. The final thing to note is that because storage is so expensive on the blockchain, which is something that we briefly mentioned in episode 2, the metadata itself isn't stored on the blockchain. The metadata itself is stored on a separate network called IPFS. And on the blockchain, all that we store is a simple URI that refers to that metadata. But we'll talk about this more in the next episode. Okay, so let's actually have a look at an FA2 compliant contract in code. So I'm going to switch back over to VS Code. I'm going to move away from simple contract that we looked at before and now go to simple NFT. Now, one thing I'm going to say first is that the contract that we're looking at here is not FA2 compliant, but it's pretty similar. And it covers a lot of similar concepts. So first of all, we're going to look at this very basic, not FA2 compliant, but pretty close to compliant contract, just to kind of understand some of the concepts. And then we're going to actually deploy an FA2 compliant contract. So this, as I say, is a contract that I wrote that is very basic. And it just, I've written it so that we can see kind of how an FA2 contract probably approximately works under the hood. So this is the contract itself. When we initialize it, we're actually initializing it with 2 objects in its storage, an ownership object and a metadata object, and both of those are empty. So we've got 2 entry points, mint and transfer, because those are the basic things that you want to do with an FA2 contract. Those are the basic things that you want to do with tokens. You want to either mint them, which means create the token, or you want to transfer a token from one to another. In the same way that if you think about in the financial world with money, if you're the 2 things that you want to do with dollar bills or pound coins is either create them or transfer them from one person to another. That's pretty much all you do with money. And tokens work similarly. So if we want to mint a token, the 2 parameters are address, which is the account to which the token will be given once it's been created, and the metadata for that token. So first of all, we find out what the ID of the token is going to be. And the ID of the token is simply just the number of tokens that already exist. So if we haven't created any tokens yet, then this will evaluate to 0. So the ID of our first token will be 0. Whereas if we've already created 1 token, then len self.data.ownership will be 1. So the ID of our next token will be 1. So we've got a 0-based indexing system where the ID of the token just goes 0, 1. That's all this is saying. And then we just set the storage. So the ownership storage at ID 0 for the first person will be set to the address that's provided, and the metadata at ID 0 will be set to that. And you can just think of the metadata as being like a URL for now. It'll actually be an IPFS URI, but you can just think of it as a URL to, let's say, some kind of JSON file that describes the contents of this NFT. So just imagine metadata is a URL or a URI. So that's all that mint does. And then transfer is also pretty basic. It takes 2 parameters, the ID of the token that's being transferred and the person who will be receiving it. So the first thing that it does is it checks if that token exists. If not, it raises an error. The second thing that it does is it checks that the current owner of the token is the person who sent, who made this, who called the entry point, and that's referred to by smartpi.sender. So this is just checking that the person who has initiated the transfer is the owner. And then if that's true, then we just change the ownership of that token to the to address. We don't need to change the metadata, obviously, we just change the ownership. And that's it. And then here I've done some brief tests. First of all, I've set up 2 users for our test scenarios. Then I've done the boilerplate setting up of the test. I've firstly verified that there aren't any owners, because there aren't any owners when we first create the contract. And then I mint a contract to Alice using this token metadata here. And then I verify that we now have one item in ownership, and that's Alice, and the token metadata for the 0th token is as we expect. And then I do a transfer from Alice to Bob, and I check that now the new owner is Bob, but the token metadata hasn't changed. I then also at the end do a transfer where Alice is now trying to transfer that token that she originally minted. But this will fail because Alice no longer owns this token. So this valid false basically tells SmartPi that when you run this test, it's expecting it to fail. So I'm not going to deploy this smart contract, and do feel free to have a look at it in your own time. We will provide a link to this in GitHub. But as I say, this contract is not FA2 compliant, but it gives the basics of what an FA2 contract achieves. So now, finally, we're going to go over to our final smart contract of this episode, which I've put under simple NFT library. And this is an FA2 compliant smart contract. Now, what it is doing is it is using a lot of inbuilt libraries in SmartPi that has a lot of FA2 functionality. So you can see here these 2 imports basically import the FA2 library and the FA2 testing library. So I haven't implemented this FA2 contract myself. What I've done is use the SmartPi libraries to say which parts of the FA2 spec I want to include in my smart contract. And then it's basically a load of boilerplate and a lot of boilerplate testing. An FA2 compliant smart contract written out in full would be quite long, and there isn't any particular value in you understanding the tiny details of it, because an FA2 contract is something that you can just deploy using libraries, and for many use cases for dApps, this will be more than sufficient. You need to get to a relatively advanced stage where you wanted to start tinkering around the edges of an FA2 compliant smart contract. So we're going to deploy this smart contract. So we're going to follow a similar process to what we did before. So I'm going to navigate to the correct directory. And I'm going to compile the smart contract. This one takes a while. And I'm going to deploy it. So I need to go to the compile directory, and I'm going to use the fa2 mint NFT directory. And I'm going to use the step 3 storage.tz and step 3 contract.tz. The storage.tz I'm going to amend so that it has my address in here. So I'm going to update this initial state here so that the owner of the contract is me and not the placeholder user that was generated. So this is in the storage file. And now I'm going to create the command. Simple NFT library. It's the name I'll give it. And here we're having to use step 003. And as with last time, we need to add the burn cap. And there we go. Our smart contract has been originated. So I'm going to copy this smart contract address and go back to ghostnet.tzkt.io, paste it in, and again we'll see our smart contract's been originated, this time with a more comprehensive list of entry points, and these are the FA2 compliant list of entry points. And the storage again is a lot more complex, but you can basically see some of the basics that you might be able to understand. Next token ID here, a map for the token metadata, and this ledger here would list out the different owners once we actually started minting some tokens. Okay, so let's go back to our slides for the final part of this episode. The last two things that we're going to talk about briefly are gas fees and security. So gas is something, the concept of gas is something that you might have heard about before in the concept of, as in the context of Web3 and blockchain. And basically gas is something that you need to pay whenever you're doing any operations on the blockchain. So each Michelson instruction that's executed, where Michelson is the low-level language of smart contracts, each time a Michelson instruction is executed, there is a certain amount of gas associated with it. Also, if your smart contract uses more and more storage, you will also have to pay a fee for that as well, which is called a burn fee. So deploying a contract requires gas and also requires a storage fee. And that is the burn fee that you saw me adding when I was originating the contracts. On Ghostnet, as we know, Tez is free to acquire, so I can originate as many smart contracts as I want, and it won't actually cost me anything. But if I was deploying to mainnet, I would have to acquire real-world Tez, which would cost real-world money to be able to originate those contracts. And a final brief note on security. When you deploy a smart contract, if there's any bugs in that smart contract, you won't be able to fix them. Smart contracts on a blockchain are immutable. The code is immutable. And this is part of the security benefits of the blockchain, is that the code, any code that is deployed there is immutable. So you can trust that if you're running, if you're calling entry points on a smart contract, the code is going to do exactly what you expect it to do because the code can never be changed. The downside of this is that if you write a bug in your smart contract, then you won't be able to fix it. The only thing you can do is deploy a new smart contract. So therefore, when you are, if you are writing smart contracts, please make sure that you test them very, very thoroughly, because you won't be able to hotfix or bug fix any bugs in your smart contract. And as the third bullet point says, when possible, avoid writing new code when there's already an existing example. So the reason that I didn't go into too much detail about how to write smart contracts is that for most use cases, you won't actually need to write any. You'll just need to be able to use smart contracts that have already been written and tested and verified many times over, and deploy your own version of that, and then build your dApp around that core smart contract functionality. And there we go. That's smart contracts, or at least a whistle-stop tour of smart contracts. I hope it was helpful, and I'll look forward to seeing you in the next episode.